Good afternoon, everyone. Am I audible? Good afternoon, everyone. Myself, Gopal Singh, standing before you to present on the topic a dual slope RDC using T network for low resistance measurement. This is not. Okay. Okay. So these are the content we'll go through, some of the brief topics. Okay, introduction. Low resistance, we mean less than 1 ohm. That is measurement that is widely used in characterization of ammeter, shunt, inductive coil, transformer, primary and secondary winding, and etc. So traditionally, we have only 3 techniques to measure low resistance. First one is the ammeter voltmeter method, second one is the Kelvin double bridge method, and third one is the potentiometer method. In all of these 3, we use Kelvin double bridge mostly in industries for high accuracy. So these are the state of the art, some of the papers that have tried to modify the conventional technique, but still they have some limitations. So what's the motivation towards it? See, Kelvin double bridge requires ratio of the arms to be fixed, which can deviate with temperature and aging. Second thing, the conventional techniques requires considerable time for manual balancing. Third, the contact resistance as well as the effect of finite resistance has a major impact on accurate measurement. And finally, achieving a true null condition also depends on the precision and sensitivity of the galvanometer. So what's the objective of it? We need a suitable correction factor considering all the nonlinear properties of the meters involved. Need to avoid bridge balancing. Okay. Third, we need to compensate the voltmeter finite resistance and also a fast measurement without manual balancing and all. So to incorporate all these things, we discover a new terminology that is called RDCs, resistance to digital converter. So what's the proposed technique? The RDC is presented here, that is used for measurement of low resistance less than 1 ohm. The scheme is based on dual slope integrator with T network in the feedback with 3 SPDT switch and a comparator. The T network consists of RX in the middle and fixed resistance and capacitor on the remaining branch. The T network boosts the input current entering the feedback capacitor, thereby increasing sensitivity, which is a novelty. During integrator charging, the lead resistance RL as well as the connecting R3, that is that constant resistance, is measured, and during discharging, lead resistance RL and the resistance, small resistance RX is measured. Finally, RL is subtracted from both sides and we get the accurate RX measurement. The scheme is independent of lead resistance RL and is a two wire type configuration, which is another novelty. And we have the simulation result which shows that it has an average error of 0.024% in the range of 0.1 to 0.9 ohm. So this is the proposed circuit. As you can see in this circuit, we have OPM OA1, comparator OC1, 3 switches S1, S2, S3, they are the SPDT switch, and the timing unit TU. As you can see initially, if switch S1 is at position 0, switch S2 is at position 0, and switch S3 is also at position 0. Since switch S1 is at position 0, minus V reference is connected to the inverting terminal of the OPM. So the arrows in the green color shows the current path when it is connected to minus V reference. You can see the current starts flowing from the integrator output V naught I, goes through the capacitor, and then it bifurcates into 2 branches followed by R3 and R1. In this case, the integrator voltage will start charging and will ramp up, and it ramp up to the threshold voltage of the comparator. As soon as it reaches the threshold voltage of the comparator output will change. Initially, the comparator output was at plus VCC. Now, the comparator output will change to minus VCC. As soon as the comparator output will change to minus VCC, it changes the position of the switch. Now, switch S1 is at 1 position, switch S2 is at 1 position, and switch S3 is also at 1 position. Since switch S1 is at 1 position, now plus V reference is connected to the inverting terminal of the OPM, and the arrow showing in the red color shows the current path when it is connected to plus V reference. So the current flows from R1 then same current goes to R2. Also, since we have a, due to that, we have a ground potential at the inverting terminal of the OPM due to virtual grounding, voltage at A is negative, and at that time the voltage near the RL2 is ground, so current will flow from high voltage to low voltage. So IX will flow like this, and finally they accumulate and passes through C1. Now in this, the second time, integrator output will now ramp down linearly to the threshold voltage of the comparator. As you see, now the switch S3 is connected to position 1, means the threshold voltage of the comparator is ground. So till ground, it will ramp down. As soon as the integrator output goes below ground voltage, again the comparator output will change, and it changes the position of the switch, and again the cycle will repeat. So circuit description: circuit consists of OPM OA1 with a feedback T network. The green and red arrows show currents represents the current path. One branch contains fixed resistance R2, and other one switches between RX and fixed resistance R3. As you can see, in the S2, we are talking about S2, that switches between RX and R3. Assuming ideal switches, current I3 is R2 by Rx or R2 by R3 times I2. Thus, the capacitor current IC is I2 times I2 1 plus R2 by, means it, the current gets add up in the capacitor current. The capacitor forms the third branch and integrates the current IC. Integrator output V0I is connected to the comparator OC1, where output is a quasi-square waveform. The charging and discharging time are measured using timing unit, that is inside a microcontroller. We measure the T1 time and T2 time. And the equation Rx gives you the relation between the T1, T2, R1, R2 and R3, where small r2 represents the switch resistance. If we are using the practical switch, they have some resistance. Now the comparator output Vc is also used for controlling the switches. That's it. Okay. So figure second, A and B shows the two different circuits. Actually not a different circuit, the same circuit. But that is the thing, we have changed the input voltage, and it shows the how the current flows through it and what are the equations. Final equation is equation 8, where Rx is equal to in terms of T1, T2. Then figure 3 and figure 4. Figure 3 shows the flow chart of the complete measurement scheme, and figure 4 shows us the expected waveform of the integrator and the comparator output. Then the simulation result. Figure 5 shows the output of the integrator and the comparator. The blue ones is the comparator output, and the orange one is the integrator output. As you can see, during the charging, the comparator output is high, that is plus VCC, and during discharging, the comparator output is low, that is minus VCC. We have used OP07, LM311 and MAX 4680 IC as OPM, comparator and SPST switch respectively. Fixed resistance R1 is 100 kilo ohm, R2 is 24.9 ohm and R3 is 1 ohm, whereas the feedback capacitor is 27 microfarad. The threshold voltage of the comparator is 6 volt, and the supply voltage given to the OPM and the comparator is plus minus 15 volt, and input reference voltage is plus minus 5 volts. So figure 6 shows the results. As you can see, during the charging time, we don't have the Rx, so every time it's remains the same, while in discharging time, we vary the Rx from 0.1 to 0.9, so we got different slopes. So rising slope, during the rising slope of V0I is 21.350 volt per second, independent of Rx, and falling slope is dependent of Rx, it gives a variable T2, and total time taken for measurement, for one measurement for Rx equal to 0.5 is 0.482 millisecond. Then figure 7a shows the discharging time versus the actual resistance that increases linearly, while figure B shows us the measured resistance versus actual resistance versus the percentage error. As you can see, as we go near to 0.8, 0.7, 0.9, the error is very less, while we go far 0.1, 0.2, the error is more. The reason is because of the feedback capacitor. If we use a high feedback capacitor, okay, the error might decrease, but because if we keep on increasing the feedback capacitor, the charging and discharging time will increase. Also, to decrease this error, we can use short lead wires. So these are the conclusion. A low resistance Rx less than 1 ohm is measured using dual slope integrator with T network in the feedback path. The T network boosts the input current entering the feedback capacitor. During integrator charging, the lead resistance RL is connected R3 and is measured, while discharging Rx plus RL is measured, and finally we subtract the RL to measure Rx. These are the references. Thank you.